Hello, folks. So this talk is on support vector machines and Radon's theorem. And this is a talk that I gave in May 2022 for the AMS Western Sectional during a special session on computational topology and its applications organized by Hitesh Gakar and Miro Kramer. So I'd like to thank the organizers and also thank them for allowing me to record this again afterwards to post to my YouTube channel. This topic is joint work with Brittany Story and Elin Farnell, and the three of us were at Colorado State University at the time of this work, but Elin is now at Amazon and Brittany is starting a postdoc at the University of Tennessee and Aberdeen Proving Grounds. I've put here the archive link. The archive URL is also in the video description below, as is a link to this PDF slides if you'd like to check those out. So I'll be connecting support vector machines, which are a classic and powerful tool in data analysis, to Radon's theorem, which is a classic theorem in convex geometry and discrete geometry. And it'll be a visual talk, so a lot of pictures explaining the main ideas. First, let me introduce Radon's theorem. Radon's theorem says that if you're in n-dimensional Euclidean space and you have n plus 2 points, then you can find two disjoint subsets of those n plus 2 points whose convex holes intersect. So here we're in the plane, n is equal to 2, so I have 4 points. And I can break them into two disjoint subsets, the blue points and the red points. And you'll notice that the convex hull of the blue points, meaning this line segment, and the convex hull of the red points, they have an intersection point. Here's another example of 4 points in the plane. Now the way I satisfy Radon's theorem is I have 3 blue points forming a triangle and 1 red point. And the convex hull of the blue points is this closed triangle, including the interior, which intersects the convex hull of the red point, right at the red point. So no matter how you draw 4 points in the plane, you'll be in one of these two cases. You should think of this as mapping a tetrahedron into the plane. A tetrahedron has 4 vertices, and if you draw it in the plane, you draw it in one of these two ways. No matter how you map a tetrahedron to the plane, you always have 2 disjoint faces of the tetrahedron that intersect once it's been mapped to the plane. So here in this tetrahedron, these were 2 edges that were disjoint in the tetrahedron, but collide now once I've mapped the tetrahedron to the plane. And similarly, in the tetrahedron, in this picture, in this map to the plane, here's a triangular face and a vertex at the front that were formerly disjoint on the tetrahedron, but they now collide when we've mapped to the plane. We'll see pictures of Radon's theorem also in 1D and in 0D. So in 1D, I now only have 3 points in the line, and I can pick 2 points to be blue and a single point to be red, so that the convex hull of the blue points intersects the convex hull of the red points. And in 0-dimensional space, which is just a point, this is saying that if I have 2 points, that collide in a single point, then those 2 points collide. You should also think of this as, mapping simplices down. So in the real line, you should think of this as we're mapping a triangle to the real line. And no matter how I map the triangle to the real line, I can always find 2 disjoint faces in the triangle, the blue edge and the red vertex, whose images collide once I map this triangle to the plane. Or in 0 dimensions where I'm mapping an edge to a single point, and I can always find 2 disjoint faces in the edge, namely the left endpoint and the right endpoint, so that when I map the entire edge to 0-dimensional space, those 2 disjoint faces collide. Okay, so that's Radon's theorem and some pictures and some examples. What are support vector machines? Support vector machines are a popular tool in data analysis. Pretend at first that we have two classes of linearly separable data. So we have points from the red class and points from the blue class, which are linearly separable. Radon's theorem finds the hyperplane, so a support vector machine finds the hyperplane that has the widest margin. Okay, so the width of the margin is the width of this road here. Okay, this dotted line is what you actually use to classify. So a new data point here would be classified as red, whereas a new data point here, here, here would be classified as blue. And you want a wide margin, so it's sort of like you have more room for error. Okay. The data points that live on the margin, these are called the support vectors. And they are the data points that really determine the direction of the separating hyperplane. For example, if I have a new data point here, that doesn't change the direction of the support, the optimal hyperplane at all. But if I have a new blue data point here, yeah, the optimal separating hyperplane would twist and would be a slightly different direction. Okay, so in summary, when you have linearly separable data, support vector machines find the separating hyperplane with the widest margin, the largest gap, and the data points that are on the edge of the road, the closest ones to the separating hyperplane, those are called the support vectors. In real life applications, you want to use a version of support vector machines that allows for misclassified data points. You don't want to only be able to handle linearly separable data, or you don't want to overfit your data. So in reality, support vector machines balance two competing effects. You want to have as few misclassified training points as possible, yet you still want a wide road. Okay. But we'll stick with linearly separable data for this talk, the simplest version of support vector machines, because that's the easiest place to connect it to Radon's theorem. So there is a classical application of Radon's theorem to support vector machines, and that's to describe the VC dimension of an affine separator. So let's say you, let me describe the VC dimension. It's the maximum number of points such that no matter how you label those points, red or blue, you can always find a classifier that recovers those labels correctly. So we're looking for affine separators as our classifiers. And in n-dimensional space, the VC dimension of an affine separator n+1. You can find a set of n+1 points, that your classifier will shatter, it's called, recover the labels no matter how you label them. But you can't do this for n+2 points. So in the plane, we can shatter collections of 3 points, so long as they're in general position. So here's 3 points. I've labeled them here 1 red and 2 blue, and you can see that I have a line that separates the red points from the blue points. If I change this point to red, I just need a different line, okay? But no matter how I label these 3 points, red and blue, I can find some line that recovers the labels. So I can shatter 3 points. But Radon's theorem can be used to prove that you can't shatter 4 points in the plane, because here's, for example, 4 points in the plane. Radon's theorem says I can always find 2 disjoint subsets, red and blue, whose convex halls intersect right here, okay? So if I had a linear separator, right, this entire convex hall would be on the red side of that separator, and this entire convex hall would need to be on the blue side of the separator, and that's impossible because they intersect. So Radon's theorem shows you can't shatter n+2 points, but you can see that you can shatter n+1 points. And that's why the VC dimension about affine separators in n-dimensional space is n+1. Okay, but we're going to look at a different connection between Radon's theorem and support vector machines. When you see pictures of the support vectors, I want you to start thinking of Radon's theorem. So here I have 3 support vectors, okay? So think of this as Radon's theorem where I have 3 points in a line, where I'm mapping a triangle to the line. My data is in 2D, but the line I'm talking about is the separating hyperplane, okay? So take the support vectors and project them onto the separating hyperplane. We had this triangle here, which we're now mapping to this line, okay? Now, when you map a triangle to a line, Radon's theorem says there is at least one labeling where the convex hull of the blue points intersects the convex hull of the red points. And our theorem will say that a separating hyperplane is optimal if and only if the support vectors, when you project to the separating hyperplane and you equip them with their labels, it forms a Radon's configuration, as you see here. There's another possibility in 2D. You could have data clouds that look like this in blue and red, okay? And here we have only one support vector on each side. So now think of this as, this is a Radon configuration in 0-dimensional space, right? I'm mapping this line segment to 0-dimensional space, and the red and the blue points collide in 0-dimensional space. So let's go up a dimension just to improve our visualizations. And this is probably the most important slide of the talk. Okay, so now we're in 3D and we have data clouds in 3D. So I've only drawn the support vectors, but really I have blue points over here, many blue points, and many red data points over here. And same thing in these other pictures, right? These are entire data clouds. Okay. And what I'm showing you is the possible configurations of the support vectors. So the separating hyperplane, is this hyperplane right in the middle in 3D. And these are the support vectors from the red class, and these are the support vectors from the blue class. And one possible Radon configuration, or one possible configuration of support vectors, is 3 support vectors from the red, 1 from the blue. When I project those to the separating hyperplane, then inside the separating hyperplane, I find this Radon configuration, where the blue point is inside the convex hull of the projected red points. Alternatively, my support vectors could be divided 2 and 2. And when I project to the separating hyperplane, okay, I'll get a Radon configuration like this, where in the separating hyperplane, the projected blue points have a convex hull, which is an edge that intersects the convex hull of the projected red points. And you can also have these lower dimensional configurations where, this is really a Radon's configuration where I'm not mapping a tetrahedron to the plane, as I did here, but I'm mapping a triangle to a line, or I'm mapping an edge to a point. So in higher dimensions, you can still have these lower dimensional Radon configurations. But in 3D, we have these other pictures that we couldn't previously see in 2D. So the theorem is that a separating hyperplane is optimal if and only if the projections of the support vectors to the separating hyperplane give a labeling satisfying Radon's theorem. Namely, we take these support vectors, we project them to the separating hyperplane, okay? And then the support vectors from the blue class, their convex hull should intersect the convex hull of the projected support vectors from the red class. let's say somebody tells you you have support vectors that look like this, where when I project, the convex hull of the projected support vectors from the blue class doesn't intersect the convex hull of the projected support vectors from the red class. Well, you know that person is misleading you, okay? This is not the optimal separating hyperplane, okay? Because the convex hulls of the support vectors don't intersect after we project, we know that we can rotate the hyperplane and get a wider road. So in this exact example, you can rotate the hyperplane a little bit, rotate it clockwise, and you get a wider hyperplane, a wider margin, where now the projections of the support vectors do intersect. Okay, so you'll actually see pictures in textbooks where folks claim that this is, an optimal support vector machine configuration, but it's not. And you can use this convex hulls intersecting criterion to verify that using our main result. So in summary, a separating hyperplane is optimal, i.e. has the widest possible road, if and only if, when you take the support vectors from the two classes and project them to the separating hyperplane, the convex hulls of the red points and the convex hull of the blue points intersect. So let me conclude by giving you just a taste of what can happen with randomly chosen data, okay? So you need a model for linearly separable random data. And the random model that we chose, which definitely affects your results, which random model you choose, is we had two Gaussians, okay? And then we sampled points from the red Gaussian and we sampled points from the blue Gaussian. And whenever we sampled a point that made the configuration no longer linearly separable, we just rejected it and sampled a different point instead. So this is sort of conditioning on the fact that we want our data to be linearly separable. So sample points from the red Gaussian, sample blue points from the blue Gaussian, but condition on the fact that you want your data to be linearly separable. And let me show you some statistics of what configurations we got. All of these configurations are possible with positive probability. And we did computational experiments. So let's do 1,000 trials in 3D. So 1,000 different times, we sample points from the Gaussians to get two different linearly separable data sets. Do that 1,000 times. All right, so many of them had only one support vector on each side. Fewer had two support vectors on one side and one on the other. But we also had configurations with four support vectors in total, either 2 and 2 or 3 and 1. Okay. This isn't so meaningful on its own because there's many different models of random linearly separable data. But what is more meaningful is let's vary the model and see how these numbers change. So we'll vary the model by decreasing the distance between the Gaussians or increasing the distance between the Gaussians. Okay. So when the distance between the Gaussians is small, you're more likely to have more support vectors. And when the distance between the Gaussians gets larger, you're more likely to have only one support vector on either side. And what's the reason for this? The reason you should have in mind for this is when the distance between the Gaussians, the Gaussian centers is small, then there's many data points, near the separating hyperplane, okay? And so you're more likely to have more support vectors. Whereas when the distance between the Gaussians is really large, right? Maybe, you could think of your data cloud as being roughly ball-shaped, then you're more likely to have sort of a unique data point, the furthest east data point from one class and the furthest west data point from another class that are the support vectors defining the optimal separating margin. Okay, so that's just some intuition when you might expect to find more support vectors or fewer support vectors. I think there's a lot more experimentation that can be done here. Let me end with some open questions. So the fiery dice problem, you take two six-sided die and you toss them and you ask, how do they intersect? Well, with probability 1, they intersect either vertex to face or edge to edge. What we're doing is we're sort of doing a fiery dice problem where the dice, we don't wait until the dice intersect, but we ask, how do things look when the dice are 2 inches away from intersecting? And then when the dice are 2 inches away from intersecting with positive probability, you can have two vertices being the closest. Okay. Kernel SVM is a way to use a kernel to map your data into higher dimensional space so that you can get a non-linear separator in low dimensional space by using a linear separator in high dimensional space. Our results give weak consequences for kernel SVM, but maybe there's stronger results one could obtain. Using the same picture, there's a version of spherical or ellipsoidal SVM where the dividing margin is a sphere or an ellipse. Think like a racetrack, separating the blue points on the inside from the red points on the outside. What's a version of this analysis or something analogous to Radon's theorem that you could apply here? Radon's theorem has a generalization called Tverberg's theorem. So don't just map a simplex, 1 dimension higher to Euclidean space. Don't just map a tetrahedron to the plane, but map a simplex that's many dimensions higher down into Euclidean space. Okay? When you have extra dimensions, you can now prove that you have maybe 3 faces that were disjoint in the simplex that now intersect once projected down into much lower dimensions. So here's an image of it from Wikipedia. Pretend we have a simplex on 7 vertices that I map down to the plane. Tverberg's theorem, I think, implies that you can find 3 disjoint faces from that simplex on 7 vertices that now have a point of common intersection in the plane. So can Tverberg's theorem be applied to say anything about the various versions of multi-class support vector machines that exist? And it'd also be nice to know if you could say things mathematically about soft margin support vector machines where the data is not linearly separable, because this is what's used in actual applications of support vector machines to data analysis. Okay, well, I'll end there. So thanks so much for your time and attention.